Hello dear students, welcome to Pen and Paper Chemistry. So let's help you overcome your phobia of numericals by doing a few questions today. Remember the pen and paper. Now try the questions that follow. So did you attempt question number 1? As I gave you the hint, the temperature has to be thermodynamic temperature. So temperature has to be in Kelvin. So T1 is 293 Kelvin, that is 20 plus 273. And I'm not taking it as 273.15 just to keep the matters easy. T2 is 313 Kelvin. Rest, what do you have to do is, you just have to input the Arrhenius equation, the integrated Arrhenius equation. Now it has also been given to you that the rate of the reaction is tripled. So that means the rate constant K2 is 3 times of the initial rate constant, that is K1. We'll substitute the value over here, EA upon 2.303 into R, 20 upon 293 into 313. Now here, a quick tip. If the value of R is 8.314, since we will be, this becomes a constant, it is good to commit it to memory and say that 2.303 into 8.314 is 19.147. So it saves your time in calculating this value. Unless you are, of course, if you are allowed to use a calculator, then that's it, it's super easy. And then also I gave you the value of log 3 because here the K1 will cancel out. So log 3 is 0.4771 and then starts the whole ordeal of multiplying. So you'll have 0.4771 into 19.147 into 293 multiplied by 313 divided by 20, which gives you the value of the activation energy in joules per mole. So we got the answer here as 41890 joule per mole. It's the unit of energy. Or you can also express it in kilojoules per mole, in which case it comes out as 41.894 significant digits, kilojoule per mole. I hope this makes it clear. How many of you could get this correct if you attempted it from the previous video? Let me know in the comment section. Now the second question was just a practice and it was exactly like the first one, wherein what you've been given is that the first is simply a statement that for every 10 degrees Celsius rise in temperature, the rate of a chemical reaction is doubled. This is what we had said. So we are going to show it mathematically as well, and we are taking a difference in temperature as 10 degrees Celsius. But again, remember that in the formula, the temperatures are in Kelvin. So convert the temperature in Kelvin, in degrees Celsius to Kelvin, plus 273 and 37 plus 273. As simple as that. Always jot down the data which is provided to you. So, and after that, so what is the first thing that you have to do is you have to write down the data. Second is you write down the formula. And third is you put down the values and calculate. So that's what we've done over here. Log of K2 by K1. Now why is it 2? Because we know that the rate constant is getting doubled. The rate of the reaction is getting doubled. So K2 by K1 is equals to EA upon 2.303 into R. Again, as I said, you can simply simplify it to 19.147 T2 minus T1 upon T1 T2. The answer is 53.60 kilojoule per mole, and if you've got it right, there you go, you've got another star in your kitty. Now the third question must have been a bit challenging if you are not allowed to use a calculator according to your curriculum. So I'm going to teach you a very easy method how you can go about it. Of course, the easiest way would be if you have your log tables with you. So anyway, you would need log tables for this chapter. So if you haven't, then please pause the video, grab your log tables so that you can understand what I'm saying, and I'm going to teach you how to see the log tables as well. So I'm going to decipher the information from the question itself, where it says that the rate constant is 3.46 into 10 to the power minus 5. So in order to save time, I've already listed it over here. At T1 298 Kelvin, rate constant K1 is 3.46 into 10 to the power minus 5. And T2, that is at 348 Kelvin, the rate constant is 4.98 into 10 raised to the power of minus 3 per second. It's a first order reaction, right? As you can make out from the unit. Again, we apply the formula. I have already substituted the values. Got it? Now comes the tricky bit. How do you put the log values over here? Now, we've already, this integral part is already given to us as 4.98 and 3.46. So, I'm going to write the characteristic. And as I said earlier, if you have not, then please watch the videos on logarithmic tables and how and what are the rules of using logarithms. You will find them very, very handy. What I am doing now is I am going to teach you how to solve this part. Here 4.98 into 10 to the power minus 3, that means the characteristic of this part becomes 3 bar. Okay. Characteristic and mantissa, I am not talking about it now, otherwise it will prolong the concept. So I will have it as log of 3.46 into 10 to the power of minus 5, right? This is just like the rules of exponents, 3.46 into 10 to the power minus 5. So this becomes bar 3 point. Now if you're asking me how did I get bar 3 over here, please and please watch the video on log tables. I've loaded separate video on log tables. Minus, now put the bracket, there's a minus sign over here. We don't want to go wrong. From 10 to the power minus 5, I get the characteristic as minus 5 over here. Decimal. Next step is to see the log value. I've got to see 49 under 8. Since we've already accounted for the decimal bit, and 34 under 6. How do we do that? Have you got your log tables ready with you? Because we are going to talk about and see how do we see the log table over here. So you see your log table looks something like this. So you've got 2 digits here, 1 here, and the mean difference over here. That's why it is called as the 4-figure log table. So 2, the first 2 digits you're going to see in this column. The next digit you're going to check in this column, and the mean difference, the 4th digit you're going to check in this column. By the way, these are log to the base of 10. Okay. So my value was 4.98. So I have got to see 49 under 8. So let's get going. I've got 49 under 8. So you see over here 8 is coming here. There we go, 49, and we go on to 8. Right? Gives me a value of 6972. So I get here bar 3.6972. take away. We had put bar 5 already. Now what do we have to see? We have to see 34 under 6. So let's get going again. So 34 under 6. 34, and we see it corresponding to 6. So this gives me a value of 5391. So bar 5.5391. How am I going to solve it? Just follow the rules of mathematics. Bar 3 means 3 of negative, and the rest of it carries the sign which is outside, and that is a positive sign, right? When we don't write any sign means a plus. Then take away or minus 5 bar 0.5390 or 91. Yeah, we got it as 91, right? And we have not yet touched the right hand side, okay? I've just left it like this. Now to solve it over here, 2 minus 1. So just how you would do in normal mathematics, just don't touch on this, just solve the parts after decimal. So 2 take away 1 is 1, 8, 5, 1. Now coming to the integral part. So here minus 5 minus 5. Bar means that the 5 is negative over here. Only this part is negative, and of course here in this part, here the whole value is negative. So minus 3 minus 5. What do I get over here? Minus 3 plus 5 gives me a value of 2. 2.1581 is my left hand side. So I've got over here 2.1581, and then we've got to find out the value of EA, activation energy. So multiplied by 19.147 times 298 times 348, and whole thing divided by 50 gives me the value of activation energy. Now again, these calculations are long, right? So many a times the students just get dissuaded and they just leave the question at this point. My advice to you would be to learn logarithms. If you are not allowed to use a calculator according to your curriculum, then learn logarithms. They will go a long way with you, and they will make the things very, very easy. So activation energy comes out as 85,703 joule per mole, or it could be 85,700 also, depending upon what kind of calculator you are using. Or we could also write it as 85.70 kilojoule per mole. I know many of you would be finding this quite confusing and maybe lost while doing the logarithms. But it all comes with practice. It all comes with practice. You will have to put in a little effort in order to understand a new concept. But believe me, physics and chemistry numericals will become super easy when you do that. Question number 4. As I had already given you a hint, you actually don't need to draw the graph, but you need to remember what does the slope indicate when you've drawn a graph of log of k against 1 upon t, not natural log. If it was natural log, then we would have done away with this 2.303. Then it would simply have been slope is equals to minus EA by R, right? Remember? So we had deciphered two things from the graph, that slope is equals to minus EA upon 2.303 R, and secondly is the log of A is provided by the Y-intercept, over here, right? So just substitute the value. You've been given the slope as minus 6680 Kelvin minus EA upon 2.303 R. As I said here, you can just simplify it as 19.147. Substitute the value, multiply, and you get the value of the activation energy. You can leave your answer in joule per mole or kilojoule per mole. What about the Y-intercept? Now log A is 6.2. It is provided to us in the question. The Y-intercept of the above graph is 6.2. What is the frequency factor? So now you are given log A. You have to find A. So what is A? If you are given log, in order to find the decimal value, you will take the antilog of this. Here you will not touch on this 6. Why? Because this 6 will tell you the power of 10. So you notice over here 10 to the power of 6. If supposing this 6 was, let's suppose I had log A equals to 6 bar 0.2. Then the value that I would have put over here is 10 to the power minus 6, because bar means a negative 6, right? Which is not so in this case. And for the integral part, you just have to see the log table. Now, how are you going to see the log table? There is 0.2 and then 0, 0, 0. So just like you saw the log table, now you're going to see the antilog table, and you will see 0.20 under 0 in the first part and then 0 in the mean difference. Of course, I don't think so. There's a 0 in the mean difference. So 0.20 into under 0 is what you're going to get. And that gives us a value of 1.585 into 10 to the power 6 collisions per second. Wasn't that easy? Grab a pen and notebook and try these questions yourself. Question number 5, and this is where things started getting tricky, because you don't have to find the activation energy. You're given that you have to find out the temperature, and you've got to deal with logarithmic values and so on. Don't worry, when I am there, I'm going to again simplify the things for you. So again, what I've done is I've just listed down the values based on the question, and I'm sure by now you've gotten used to the fact that you've got to list down the data, you've got to put the formula and then substitute the values. Now, how do I simplify these values? See over here, 15 times 3 is 45, and this is 10 to the power 4, this is 10 to the power 3, so I have 10 over here. So I am left with log of 10 by 3. See, I'm going to solve it without even the log tables. I'm just dealing with the left hand side. So I've got here, this can be written as log of 10 minus log of 3. Log of 10 to the base of 10, because we are dealing with logarithms to the base 10. Any number to the same base is always 1. Remember your rules of exponents. A to the power 1 is equals to A, right? So here this will be 1. Log 3, 0.4771. Remember, I told you to memorize these two values in the previous question. Now again, just go on doing the question like you would do for normal mathematics. Subtract. 10 take away 1, 9 minus 7. Please help me, I've forgotten my mathematics. Correct. So we get here 0.5229. Pretty simple, right? And then what you have to do is, so this whole part is taken care of, and we get the value of 0.5229 0.229 is equals to 60 into 10 to the power 3 upon 19.147. Where did the 19.47 come from? Yes, the 2.303 into R. And you notice something over here. I have not put it as T2 minus T1 upon T1, T2. I have kept them as separate because I need to determine T2. I don't want to complicate things over here. So I will leave it as 1 upon 283 minus 1 by T2. Go ahead. Let's solve this further. 0.5229 times 19.147 divided by 60 into 10 to the power 3 is equals to 1 upon 283 minus 1 by T2. Right? So again, what you can do is you can solve this part either by multiplication or by logarithmic tables, and I got the value like 1 by T2 is equals to 0.000166. I left the 1 by T2, I took it as a variable, kept it on one side. We simply apply the rules of simple equations, and then 1 by 283 minus this value gives us 0.003366. Of course, I'll be honest here, I've done it with the calculator, but you are, if not allowed by your curriculum, you have to use the log tables, but I'm confident that you will reach the answer. So T2 is 297.02 Kelvin. Since in the original question the temperature value was given to us in degrees Celsius, remember? That is why it is better that we also leave our answer in degrees Celsius. And how are you going to do that? Yes, take away 273 from it and you get it as 24 degrees Celsius or 24.02 degrees Celsius as your answer. Tired? Take a deep breath. Relax. Nothing is difficult. Just keep a positive attitude that yes, you can do it. When you have come so far, you will be able to do it. Let's see the sixth question now. Now this was a pretty simple and direct question. Decomposition of a reaction follows the equation this. Calculate the activation energy and the collision frequency, right? Nothing tough about it. So let's get going. You just compare it with the basic Arrhenius equation where you had K is equals to AE to the power of minus EA, that is activation energy, upon R into T. You see over here K is equals to 4.5 into 10 to the power 11 per second. So of course that's our collision frequency. Gives us our first answer, the value of A, that is collision frequency, a pre-exponential factor. So I can directly put A as 4.5 into 10 to the power 11 collisions per second. That is why if you notice it has got the unit just per second. Now coming to the next bit of it. E to the power minus EA by RT. In other words, this minus EA by RT is this expression over here. Why is this Kelvin minus 28,000? Could you figure out? I struggled. I got confused for a while. Why is the activation energy given in Kelvin? But then realization dawned, because this minus 28,000 Kelvin is actually the value of minus EA by R. Right? Because we've got minus EA by RT is equals to minus 28,000 by the temperature. Of course, we don't need the temperature over here, so we can, keep our tensions a bit low. Then, if you compare the units, my activation energy is in joule per mole, whereas the value of R is joule per mole per Kelvin, or more appropriately, joule per Kelvin per mole, right? Yes, absolutely. That is why the value of minus EA by R will be in Kelvin, right over here. So now it's pretty simple. You can just put the value of R and you get the value of. By the way, many as times the students struggle to understand whether we put the value of R as 8.314 or 0.0821 or sometimes 1.987 calories. You see, we are dealing with energy over here. You look at the units, joule per Kelvin per mole, right? So look at the units. You're talking about energy units over here. So you will use the value of R corresponding to this. 0.0821 is liter atmosphere per mole per Kelvin, or if you are dealing with bar, so here this would be in volume. So try to understand the logic behind it rather than just memorizing it. So we get the value of activation energy as 232.79 kilojoule per mole. Now just now I shared my experience with you that I was confused why they are specifying as Kelvin. Yes, we are all human beings. We tend to get exhausted at times, and in such occasions it is good to take a deep breath in and relax. Question number 7. Actually, I was quite confident that you would be able to do it. Probably some of you may have struggled in the B part, but A and C were pretty easy. So let's see how to do it. If you see over here, it's given the rate constant is given by the expression. So I simply am going to equate it to the logarithmic form of the Arrhenius equation. So log K is equals to log A minus EA upon 2.303 RT, and that is in Kelvin. So you have to find out the pre-exponential factor for this reaction. So log of A is equals to 14.34. What are you going to do to determine A? Yes, you take the anti-log, correct? Okay. Again, when you see the anti-log, remember this 14 is 10 to the power of 14. What you have to see in the anti-log is 0.34 under the column of 0. And I get it as 2188. So putting the decimal, so 2.188 into 10 to the power 14. Please don't forget the units, and it is collisions per second. So what we've done the third part first, no problem. Let's do the first part now. Talking about the activation energy. Yes, go on, equate these, right? You get the value of activation energy as 239.34 kilojoule per mole. Good going so far. Now we have to come down to the second part, the B part, which some of you must have got very easily if you have been revising the equations thoroughly, right? You remember we had given the formula that for a first order reaction, rate constant is given by 0.693 divided by the half-life period, right? Now in this question it says that the half-life period is 256 minutes. We are going to convert those minutes into seconds. Why are we converting those minutes into seconds? You see over here in this formula, in this we've taken the value as per second, collisions per second, right? So we have to convert this also into second. So this gives me a value of 4.5 into 10 to the power, something like that. Are you getting like that? So 4.5 into 10 to the power minus 5. Are we there? And what will be the unit? Per second. Correct. It's a first order reaction. We have to go now to the next step. So we have to determine the temperature corresponding to this rate constant. So log of K is equals to log of A minus EA upon 2.303 into R, which I'm going to simply write it as 19.147 into the temperature in Kelvin. Okay, just realize that we've already been given the value of log K. Sorry. So log K is 14.34 minus 1.25 into 10 to the power 4 upon T Kelvin. So our log A is taken care of. Activation energy is taken care of. You just have to find T. But again, the real sore point is the log. So again, I'm going to teach you how to solve the logarithmic bit of it. So log of 4.5 into 10 to the power minus 5. So here again, see 45 to be seen under 0, right? So 45 under 0, what do you get the value? 6532, correct? This is again from the log tables. And what about the minus 5? That becomes the characteristic. So my log of 4.5 into 10 to the power minus 5. Now this minus 5 becomes bar 5, and 45 under 0, we got it as 6532, right? Now how are we going to deal with bar 5? The teacher is making things more and more complicated. Don't worry. Stay relaxed, stay calm, we will be there. So we've got here 5 bar 0.6532 is equals to 14.34 minus 1.25 into 10 to the power 4 upon temperature. So 1.25 into 10 to the power 4 divided by the temperature is 14.34 minus bar 5.6532. See, I am applying the basic rules of algebra. I am simply doing mathematics, nothing extraordinary. So 14.3400, take away bar 5.6532. What do you get over here? You have to subtract. 10 minus 2 is 8. 9 minus 3 is 6. 13 minus 5 is 8, and 12 minus 6 is 6. Now come to the confusing bit. Now here we had borrowed. Remember, we are left with 3 over here. So 13 minus 5. I get here 13 plus 5 gives me a value of 18. Simple. So 1.25 into 10 to the power 4 upon the temperature in Kelvin is 18.6868. Rest is easy, right? You just have to divide 1.25 into 10 to the power 4 by 18.6868. The answer, 668.92 Kelvin, or if we convert it into degrees Celsius, we take away 273 and we get the answer as 395 degrees Celsius. You must pat your back if you've come so far and you are staying relaxed and you are able to understand and you are developing interest in the topic. Well done. Question number 8. Now this question involved your knowledge of the first order reaction, the equation of a first order reaction, as well as your knowledge about the Arrhenius equation, right? That is why I said let's leave it to handle a little bit later, and I gave you time to try it yourself, right? So let's get going. First of all, you need to understand that 10% completion means if you started with an initial reactant of 100 concentration mole per liter, what you are left with is 90 moles per liter after the given time at 298 Kelvin. Whereas 25% completion would mean A naught is equals to 180. That means concentration after time T is 75 moles per liter. Also recalling the equation of a first order reaction, T time is equals to 2.303 upon T log of A0 by AT. Now in this question you have been given that the time required for 10% completion at 298 Kelvin is equals to the time required for 25% completion at 308 Kelvin. So time required for 10% completion at 298 Kelvin is the same as the time required for 25% completion at 308 Kelvin, right? I can simply substitute the values over here, 2.303 upon K1, let me say, log of A naught. That means if I started with an initial concentration of 100 moles per liter, I am left with now 90 moles per liter. This is equals to 2.303 upon K2. That means the rate constant at 308 Kelvin. Log of 100 divided by 75, right? Okay, now if you notice 2.303, 2.303, I can just forget about it for now. To make my calculation simpler, actually I had carried K2 to the left hand side, which we can avoid at this point of time. So what I'm going to do is simply solve the log values first. So this gives me a log value of 100 minus log 90 is equals to 1 by K2 into log of 100 minus log of 75. Now log of 100, again correlated to your knowledge of exponents. Log of 100 to the base 10 is equals to x. Now 10 to the power x is equals to 100, meaning to say 10 to the power 2 is equals to 100. Or if you don't want to get into that depth, just remember log 100 is 2, log 1000 is 3, log 10 is 1. Yes, some of us are happy to simply memorize, right? So 2 minus. Now look for 90, the value of 90 under 0, and you will get it as 0.9542. No, sorry, actually we can make it simpler even, because what we can do is we can just do away with the ones, so our calculations become even easier. We don't, because for 90 we'll have to put the characteristic. So log 10 is 1 and log of 9, that means look for 90 under 0, 9542 is equals to 1 by K2 again. So you will have 2 minus, because it's 75, the characteristic will be 1.8750. So I get over here K2 by K1 is equals to 0.1249 divided by 0.0458. We leave it as a value 2.7227, depending upon what method you are using, whether you are using a calculator or you are doing it manually. The value at the third or fourth decimal place may be slightly different. Don't worry, don't panic, stay relaxed, you are doing great. Now we have to determine the activation energy. So we can use the integrated Arrhenius equation. Log of K2 by K1 is equals to EA upon 2.303 into R. You recall, what did we put it as? 19.147. The difference in the temperatures is 10, and you have the two temperatures at 298 and 308 Kelvin. Now here, please remember, there's a small point to be taken care of. In this particular question, the data gives you the value or talks about the values at 298 Kelvin and 308 Kelvin. Whereas it is asking you for the rate constant at 318 Kelvin, right? And we are going to assume that the activation energy remains constant for the entire reaction irrespective of temperature. So we get over here log of K2 by K1. Now that is why I did not solve it further, because I know that I will need my K2 by K1. So log of 2.72, sorry, I substituted the wrong value here, just corrected it, 2.7279. So that's the value I'm going to put over here, 2.7279. And we will determine the activation energy by substituting the rest of the values. Now you already know how to determine the log value. So we get the value of activation energy over here as 76569.4 joules per mole, or we can also write it as 76.569 kilojoule per mole. Again, the values may differ slightly depending upon to what decimal place you are taking. Are you using a calculator, or you are using log tables, or you are doing manual calculation? Now we've got to determine the rate constant at 318 Kelvin. So we are going to apply the equation for the Arrhenius equation. Log of K is equals to log of A minus the activation energy, whatever you have calculated, divided by again 19.147, because it is 2.303 into R. But this time the temperature is 318 Kelvin, right? So just be careful about that. When you calculate K, now here you'll first get the value of log K. Whatever value of log K you get over here, you take the anti-log of it in order to determine the value of the rate constant of the reaction at 318 Kelvin, which comes out to 1.05 into 10 to the power minus 2 per second, or your answer could also be 1.06 into 10 to the power minus 2 per second. As I said, the value depends upon how you are calculating and how many significant figures you have taken in your calculation. Right? Are we there? So this brings us to the end of the 8 numericals that we dealt with based on the concept of Arrhenius equation. Some of the questions were taken from the NCERT textbook, whereas some questions I had changed the numerical value in order to give you a chance to practice more questions. We shall be continuing with this topic. We are not yet done. We are yet to do the collision theory and, of course, catalysis. How do catalysts affect the rate of a chemical reaction? So stay tuned, stay subscribed, and more than subscribe, please share the channel with your friends if you found that you were helped by it. The only thing is we need to spread more joy around by sharing our happiness. That's the need of the hour. Stay happy, stay healthy.